Hello everyone. Today we're going to start with uh, the discussion of function analysis. So our first topic is about the general metric space. Okay, let's first recall the definition for metric space. We see that the XD is a metric space if this X is a set. It's a set of points. And this D is a mapping that can take any 2 points in this set X and return a real value. Okay? And this D must satisfy the following conditions. The first is a positive definiteness. That means no matter which 2 points you take, it's going to return a non-negative value. And also, the value is equal to 0 if and only if the 2 points are the same. The second condition is the symmetry. Which means that take the distance or metric between x and y, that's the same as the distance between y and x. And the third one is called the triangle inequality. And this is that for any 2 points, x and z, the distance between them is less than or equal to the distance between x and y plus the distance between y and z. Okay, and in this case, the d is called a metric or distance, and is motivated by the distance we studied or we learned from Euclidean space. But right now, this x can be a general set, and as long as your d satisfies these 3 conditions, then we can call it a metric. And in this case, x and d together is a metric space. Okay, so this is what you probably have seen before. So let me just give a few simple examples. The first example is the most common one, which is the Euclidean space. So remember that in Rn, it's just a set of points or set of vectors such that each component is in R. And in this case, we can define the distance between 2 points to be the x1 minus y1 squared plus all the way to xn minus yn squared, and take a square root. Okay, this is the standard Euclidean distance, and that is a metric on the Rn. And this x and y, so the x is just a vector of these n components, the y is the vector of these components. Okay, that's what the components mean. Okay, so that's probably the simplest example for metric space, but we're going to study more complicated ones in this class because our subject of interest in this course is about functions. So our X will be a space or set of functions, and we're going to evaluate the distance between functions. So let's look at this example. So here I have C of AB. That means all the continuous functions defined on the interval AB. So this basically means the functions, that is a mapping from the interval AB to a real number, and this function f is continuous. And we can define a distance on this set. So this is going to be our x. This is going to be our x. We're going to define a distance on this set, which is going to be a distance between two continuous functions, x and y. And we define it to be the maximum of the difference between the two functions. Okay, so here, this f is like a function that mapping t to f of t. This t is a point between A and B. And now for any two given functions, x and y, which plays the role of this f here, we can take the difference and say I have, this is my A, this is my B, and one function looks like this. This might be my x of t, and then I may have another function with y of t, and taking the absolute value, absolute value of the difference, then I will be able to get something like this. Okay, and the maximum value of this function over the entire interval is called my distance. This is it's easy to show that this is going to be a distance since it satisfies all these three conditions. And I'll ask you to try this by yourself and convince that this is actually a distance or metric. Okay, so the importance of the distance or metric for metric space is that it's right now the X is not simply a set with a bunch of points, but we actually can discuss the relationship between the points. And one of the most important relationship between them or about them is about convergence. Okay, so I'm going to define what is the convergence since we have the metric or the concept of distance now. So suppose I have a sequence of points which are from this set X. Okay, I usually use this notation here to denote the sequence. So you already can see the difference between a sequence or a set, which is using the same notation, but you can, as I said, you can tell the difference when we proceed, so it won't be cause any confusion actually. And so we say that the sequence is convergent or converges to a point X. Let's see that. If the distance between xk and x goes to 0 as k goes to infinity. Okay, or usually we can write this as the limit of xk and x is 0 as k goes to infinity. Okay, this is what we mean by that the sequence is converging, okay, or the sequence is convergent. If you cannot tell what is the limit, but at least you can tell if it is convergent or not. And if it's convergent, it's supposed to converge to some point like this. And we know that by this, the formal definition is to use the epsilon delta language, which says that for any epsilon, there exists a integer k, and this integer should depend on the epsilon. Okay, and it is an integer such that the distance between xk and x is less than epsilon or epsilon for all k k bigger than or equal to this k. Okay, so that's what I mean by a sequence convergent to X. All right, now let's look at the examples before. I will not discuss the trivial example, so because you all know that what that means. But look at the second example about the space of continuous functions. Then what is the convergence mean here? Okay, in this case, the distance goes to 0, means that if we are going to replace this by xk, this is by x, then the maximum value between of the absolute value between the distance between xk of the distance between xk and x is going to convert to 0. Okay, and by that, what do we mean? If we're going to follow this definition, we'll be able to see that this is a uniform convergence that we learn in analysis. Right? Because for any epsilon or epsilon, there exists a capital K such that the distance between xk and x is less than or equal to epsilon. And this d is defined to be the maximum value of such thing, right? And so for any point t, it doesn't matter which point it is from this interval, it's going to be less than or equal to this value, since it's going to be, this is the distance taking the maximum of that. So this is going to be less than, greater than or equal to skt minus xt, right? For any k greater than or equal to k, and for any t in the interval ab. Okay, since this one is bounded by the maximum value you can ever get, and that is less than epsilon. Okay, I should use strictly less than. And you know that this is the definition for uniform convergence. You have a sequence of continuous functions, and they converge to the function x uniformly. Okay, so that is one of the major concepts in metric space. We can talk about convergence. There are many other things. As you know that since we have the metric defined, then we can define the closed set, open sets, compact sets, things like this. Okay, and actually, for example, we can define the closed set based on the convergence. Okay, for example, we have a metric space, and the subset E of the space, so E is a subset of X. We said this E is a closed set if whenever we have a sequence of points from X and they're known to be convergent to some point X, then their limit X must be also in X, must be also in this space. Okay, so that's what I mean by a closed set. Okay, so you probably have all seen this before. I'm not going to talk about more details on that. We see a sequence is Cauchy. if for any epsilon greater than 0, there exists some k. Again, this k depends on such that the xk minus xj, or I should use the distance, it's going to be less than epsilon for all kj greater than equal to this capital K. Okay. By introducing the Cauchy sequence, we can define the completeness. We say the metric space is complete if every Cauchy sequence is convergent. All right, so this is a very important concept. Remember that if we just have a metric space, and then we say we have a convergent sequence, but eventually the sequence converges to some point not in this space, then it's really hard to study the property of the sequence. Because usually when people use the sequence, they're trying to get the sequence to converge to something that, and the limit is what we're interested in. But if the limit is not in the space we're working on, then that's usually is pointless, right? So in most of the cases, we will be interested in learning or working on a complete metric space, meaning that if we can prove a sequence Cauchy, then it is guaranteed that they are convergent, and their limit is inside the X, inside the space we're working on. Okay, so this is a very important concept, and later in this course, we will see in many of the cases, we'll be working on, or most of the important results only hold for complete space. They may not be true for incomplete spaces. Okay? But some are still some of them still hold for incomplete space, but we need to specify in which case the completeness is important or is necessary, or in which case it's not. Okay, and again, we're going to give a few examples. And since this is a very important concept, I'm going to particularly interested in the example I just mentioned about the continuous functions. So apparently the Euclidean space are complete. So I will not talk about that. But let's look at the space of continuous functions I mentioned earlier. This D is the definition we had earlier. It's right here. Okay, I'm going to use this as my distance or metric. Then we can show that this space is actually complete. Okay. To show that, the only thing we need to do is to recall the definition. We want to show it is complete, then we just need to show that every Cauchy sequence in this space is convergent, and their limit is also in X. Okay, I should say that here. Okay, just to prove that, let's say I have a Cauchy sequence right here. Okay, and by that, what do we mean by that is for any epsilon greater than 0, there exists some k that depends on the epsilon, such that dxk xj defined to be the maximum of the xjt minus xkt, should switch It doesn't matter. For t is between a and b, this should be less than epsilon for all the k and j greater than this capital K. Okay, so that's the definition. And let's see why this implies that the sequence is convergent and the limit is also in this space. Well, let's look at any specific t. We know that for any specific t or specific point t, we know that the xkt minus xjt is less than or equal to this d, right? Because the distance here is defined to be the maximum of those values over all the possible t's. So if you pick up a specific t, that has to be less than or equal to this, and that is less than epsilon for any k, j, greater than or equal to d capital K. Okay, what this tells us is that, remember that we have a fixed t right now, and we have a sequence of real values or real numbers defined by that. Right? Because for the fixed t, we can just look at this. This is a sequence of numbers or sequence of real numbers. And what this tells us is that this sequence of real numbers is Cauchy, because for any epsilon, there exists some k such that this is less than epsilon for all that. And this is a sequence of Cauchy sequence of real numbers. Well, we know that the set of real numbers is complete. So if this is a Cauchy, then that means they must be convergent to some point. Okay. Now we know that this is the convergent sequence for every given t. And now let's just define the limit to be x of t. So let xt to be the limit of xkt. Okay, so what do I mean by here is that I know for every fixed t, this is going to be a sequence of numbers that is convergent. Let's just call the limit of that to be x of t. The reason I'm doing this is because when I change the t here, or I change the t here, I'll get another sequence, and I'll get another limit as well. And I'm just going to call or define this function x of t to be the limit, and it changes along with this t. Okay, but anyway, this will be a valid function because for every t, I'm going to have a definition for that since this limit exists. Okay, and now the only question is, I know that this sequence is actually convergent. I look at the sequence of functions, xk, I know that it's going to converge to this x pointwise. But the question is, if this x is in C. Okay, apparently this xk is converging to x because that let me go and show you that the distance between x, k, and x. This is supposed to be the maximum of xkt minus xt. Okay, so what I know about this is that for every fixed t, For every fixed t, we know that this xk of t minus x of t, this is less than equal to, or this is equal to the limit of j going to infinity of xkt minus xjt, right? And I know that the right-hand side is less than equal to the, if I just ignore the limit, for the inside, I know this is less than equal to the xk, xj. Just taking the limit. And for each of this, I know that when j is large enough, in particular j is greater than or equal to the capital K, this is going to be less than epsilon, right? So if I take the limit, then it will be less than or equal to limit, equal to epsilon. Okay, so that means for every fixed t, I know that this is less than or equal to epsilon. Okay, and the key is right here. We know that for every one of this is less than epsilon, but when we take the limit, we can only guarantee that it's less than or equal to epsilon. So I know that this is less than or equal to epsilon for every fixed t, and then so the maximum of them will be also less than or equal to epsilon. Okay, so that's why this would be also less than or equal to epsilon, and the reason is because of this. Okay, that's the reason right here. Okay, now I can see that the distance between xk and kx is less than or equal to epsilon. So what we have achieved so far is that for any epsilon, there exists some k such that this distance is less than or equal to k, less than or equal to epsilon for all the k greater than or equal to the capital K. Okay. So that shows that the x is indeed the limit, and because we have because this convergence right here in this space is a uniform convergence, so I know that the uniform convergent to x over this interval, closed interval AB, which is compact. So we know that this x must be also continuous. Okay, I should just write this stuff without the d. Okay, and know that this is the uniform convergence of sequence of continuous functions. So I know that this must be continuous as well. Okay, so that's how we show that the space C AB is a complete space. Actually, what's important here is to notice that this space is continuous because of the way we define this distance or the metric. If we're not using this metric, this space may not be complete. And one particular example is that if we define this distance to be the integral of this, and then this space is not complete anymore because we just changed the distance. Okay, so we're going to talk about this later, but in the later of this class, we'll see that we'll consider standard space C of AB. That means we're using the metric we just said. Okay, this one, or you could use this like this. Okay? And in this case, we know that it's a complete space. Let's consider a mapping between metric spaces. Suppose I have two metric spaces. One is XD, and the other one is Y rho. consider mapping T from X to Y is called continuous. Means that it's continuous over the entire X. If for any X and any epsilon, there exists maybe let's just say this. If I know that a sequence converges to X, then I would say this. If I know that this sequence converges to X, then the T of X, xk must converge to T of X. Okay, so I'm going to rephrase this. We say that the mapping T is continuous. If you know that sequence xk converges to X, then the T of xk must converge to T of X. Is equal to 0 as well. If this is the case, remember that this metric is evaluated in the space of X, so we're going to use the difference distance D here. And this is in Y, because these 2 points are in Y now. So we're going to evaluate their distance by this rho. Okay? So if this goes to 0 implies this goes to 0, then we say the mapping is continuous. Okay. Now, a more properly or more common way to define this, as you know, is to use the epsilon delta language. And we'll see that these two are actually different, equivalent. So we have a T that is a mapping from this metric space to the other metric space, which that is continuous if and only if for any epsilon and for any X, there exists a delta, and apparently this delta depends on the epsilon and X, such that the distance between rho, distance between T, X, let me use this X0 right here, maybe it's easier. So for any epsilon greater than 0, for any X naught, there exists some delta that depends on the epsilon and X naught, such that as long as the X is close to X0 or X naught, this 2 is less than epsilon. For any, say, X, I could either say that the distance between X and X naught is less than delta, or I can say that this X is in this ball centered at X naught with the radius delta. Okay, so this one here means that the distance between X and X naught is less than delta. Okay, so this just means that the X is in the open ball centered at X naught with a radius delta. Okay, your X will be somewhere in this open ball. Okay, so that will be the same meaning. So we say that this mapping is continuous if and only if this is true. Okay, let's see how do we prove this. Okay, suppose that we know this is true, and we're going to show that suppose we know this is true, we're going to show that this mapping is continuous. Okay, let's say if not. If it's not continuous, that means I will have a sequence of points that convert to convert to x, but the t of xk is not converted to t of x. Okay. Okay. Let me not use this. I just directly prove this. Suppose I have a sequence xk such that sequence goes to x. Or in other words, I know that this goes to 0. Okay, if this is true, then for any epsilon greater than 0, I know that there exists some k such that the distance between this xk and x is less than delta for any k greater than or equal to d capital K. Okay, and since this is less than delta, it's the delta here. I know that this is going to imply that the distance between txk and tx is less than epsilon. Okay, if you like, you can use this x naught to be consistent with the right hand side we had. And you can see this, and this means that the sequence txk also converges to tx naught. Okay, and this means that the t is continuous. The other direction, suppose we know the sequence is continuous. And let's see that how do we show the right hand side? Suppose not. So the right hand side says that for any epsilon, any x naught, there exists some delta such that this is true. Okay, and if this is not true, if the right hand side is not true, then we know that there exists some x naught, epsilon naught, and some x naught, such that for any delta, let's say for any k, there exists some xk such that the distance between the xk and x naught is less than 1 over k, but the distance between txk and tx naught is bigger than equal to epsilon naught. Okay, so that's the reverse statement of this. And what happens is that, now look at the sequence we just got for each k. You can construct the sequence by increasing this k. And this sequence converges to x naught. The reason is because xk and x is less than 1 over k, and that is going to 0. It's approaching 0. But this is still greater than epsilon naught. So this txk is not really converging to tx naught. And that is contradiction to the continuity of T. And that is why this thing cannot happen. Okay, we cannot really have this. And that means this statement right here is correct. Okay, so with the definition of continuity, we actually can see that a continuity of a function will be very important when we study the convergence. Say if we know that a sequence is convergent and the mapping is continuous, then we know that after the mapping, the sequence is still convergent. And we actually know where the limit is. That's just applying this t to the limit of the original sequence, and we'll get the limit of the transformed sequence. Okay. Now we're going to introduce the most important concept in this section or in this today's lecture is about the contraction or contractive mapping. Okay, so it's a special type of mapping, and we're going to show that it's continuous, but it's more than just continuous. It has very powerful property. So let's say we have a mapping between two metric spaces. So these two are metric spaces. We call this mapping contractive. If there exists some theta between 0 and 1, strictly between 0 and 1, okay? Especially it must be strictly less than 1, such that no matter which 2 points you pick up from the space X, the distance after the mapping is going to be less than, just write it right here. For any 2 points you pick up from the space, the distance after the mapping, you know that this is in the space Y now, so we're going to use the rho here. This distance less than or equal to theta times the distance between the original 2 points. Okay, and this is called contractive mapping. Okay, so roughly what that means is that we have space X right here, and we're going to map this to space Y. And if I have 2 points, and we measure their distance, after the mapping, this point is mapped here, this point is mapped to here. Now I measure the distance again. I realize that the distance right here is less than or equal to theta times this distance, but theta is strictly less than 1, so it's strictly less than this one right here. Okay, so this is called a contractive mapping. And it will be very easy to show that the contractive mapping is continuous. The reason is if you can show that the xk convert to x, which means that the distance between the two is going to 0, then you multiply by theta, and then you know that it's greater than or equal to txk and the tx. So this will be also converging to 0 as well, and that means txk converges to tx. So if the sequence, if the mapping is contractive, then it must be continuous as well. Okay, it's very strong. So the contraction is a very strong property. Okay, with the contractive mapping, we have a very important result called the Banach fixed point theorem, sometimes called the contractive mapping theorem or contractive mapping principle. Okay. And that is a major topic or very powerful tool that we're going to use in this course. Okay, the Banach fixed point theorem. Actually, you probably have seen different variations of this theorem before. And, the main idea is that we're trying to get a fixed point of some mapping. we can generate a sequence by iterating something like this. Okay, just start from some initial guess x0 and then generate the next x1 using this mapping, and then generating next 2, so on and so forth. And if the sequence is going to converge, then this will be converging to a lambda point, fixed point. That's a very common strategy. And now we formalize this in this Banach fixed point theorem. We suppose that the x is a complete space. It has to be complete, otherwise the limit may not be inside x. Okay, so it has to be complete. And I have this T that is a mapping from x to itself. It is contractive. Then there exists a unique fixed point of T on this space X. There exists a unique X such that Tx is equal to X. So this means that the X is a fixed point of T. Okay, and the Banach fixed point theorem says that the such point, if T is contractive and the X is complete, then this fixed point must exist and it must be unique. Okay, we're going to first show that this fixed point exists. Okay, so the first step, let's pick some x0 arbitrarily from the space, then generate a sequence as I just mentioned. Xk by iterating xk plus 1 equals to txk. Okay, so we start from the initial guess x0, and then we generate a sequence like this. Then what we can see is that for any k, we know the distance between xk plus 1 xk is going to be, you know that this is equal to, according to the definition, is equal to t of xk, and the xk is equal to t of xk minus 1, right? And according to, since that t is a contractive, we know that there exists some theta. Let's say that theta is the one for the contraction. We know that this is less than or equal to theta times the distance between xk and xk minus 1. So I reduced the k by 1 from k plus 1k to kk minus 1, and I extract 1 theta. So if I keep doing this, I'll extract more and more theta. So by keep doing this, we can show that this is the theta to the power k, the d of x1, x0. Okay, so we know that for any k, I can do this. Then for any integer p, I'm going to look at distance between xk plus p and xk. So now the gap between these two is larger. It's arbitrarily large by this gap p here. And we can use the triangle inequality to reduce this to consecutive distances. So I know that this is less than or equal to dxk plus p and the dxk of xk plus p minus 1. And then the next all the way to the dxk plus 1 and xk. I know that if this is k plus 1 k, I know that's less than or equal to this. If it's the next one right here, right before this last term, then I will have the theta to the power k plus 1, right? All the way to this one, which is theta to the power k plus p minus 1. Okay, so I can rewrite this. then they have the common factor x1, x0. Okay, so that is just a part of the geometric sequence. I know that this is just equal to theta k over 1 minus theta, okay, or less than equal to that, times the dx1, x0. And the point right here is that this is a fixed number, this is a fixed number, and this is approaching to 0. So as long as k is sufficiently large, I can make this arbitrarily small. It doesn't matter what this p is. So that's why the sequence right here, generated by this iterating procedure, is going to be Cauchy. Okay, again, the reason is because for any epsilon, there exists k large enough such that as long as this k is bigger than that k, then this can be arbitrarily small, this can be less than epsilon. And it doesn't matter what this p is, as we just mentioned. And the key is that if p is super large, then you just have more and more terms, but this geometric sequence starts from the theta k. So that's the infinite sum. Now we have a finite sum, but the infinite sum will be still less than that. Okay, and that is independent of p anymore. That doesn't depend on p anymore. Okay, so this is Cauchy. And since this X is complete, now you can see that why we need the completeness. Only if it's complete, I can say that the sequence is convergent. It converges to some X in the space X. Okay, so now what we know is that the xk converge to X, right? And the txk which is xk plus 1, and that's also convergent to X because the whole sequence converges to X. Okay, so on the one hand, I know that txk converges to X. On the other hand, I know that t is continuous. So when xk converges to X, then txk should converge to tx, right? Since t is continuous, we know that when xk goes to X, the t of xk must go to t of X. And now that I know that the sequence converges to X, and at the same time it's converged to Tx, and that means X must be equal to Tx. And that means the limit point is actually a fixed point of T. Okay, this finishes the proof of the existence. And now let's look at the uniqueness. Let's suppose that I have two different fixed points. So X and X prime are both fixed point of T, but they're different. And in this case, let's apply this T to X and also T to X prime. And then we evaluate or measure their distance. And according to the, because T is a contractive mapping, I know that this is less than or equal to theta times d of X and X prime. Since theta is between 0 and 1, I know that this must be less than dx x prime, because X and X prime are different. This is a positive number, and when I multiply a positive number by some number between 0 and 1, I'm going to get a smaller number. So that's the smaller number we have compared to the original one. Okay, but on the other hand, I know that the, sorry, this is a D. We do have another space actually. So on the other hand, I know that X and X prime are both fixed points of T. So that means Tx is just equal to X, and Tx prime is equal to X prime. So this left-hand side is nothing but just X prime. And now I have some number that is strictly less than itself, and that is a contradiction. And this contradiction is because tells us that we cannot have two different fixed points. So that's a contradiction. So we know that the fixed point of T is unique. Okay. So we probably have you probably have seen something like this before, and now we're just going to formalize this, and this can be really powerful because what we really need is just a complete metric space and a contractive mapping, and then we can get this fixed point. And the reason why we are interested in fixed point is that many cases that solving a problem, solving an equation is actually equivalent to finding a fixed point. For example, if I'm trying to find the solution for this function, this x can be arbitrary in the space x, because x is right now is a metric space, so we're not just limited to Euclidean space. It could be some general space of functions even. This x could be a function, and then we're studying the property of this. We're trying to find a solution for this functional, which maps some function to a zero. And in this case, finding the solution of this is equivalent to finding, say, I add this x on both sides or subtract x on both sides. It's like this, right? So if I define my t to be the identity minus the phi, then finding the solution x of phi is equivalent to finding the fixed point of t. Okay, so these two are actually equivalent, and in many cases we can just convert the problem, like solving this into the problem finding the fixed point of some other modified function. Okay, I'm going to show this example right below. You can see how powerful it is. So let's see application. So application is we're going to consider the existence and the uniqueness of a solution of ODE. Consider the ODE problem. So this is a typical initial value problem of ODE. That means we're given a ODE, or the x prime, use x prime. The derivative of x, so x is let me make this even simpler. Just start from 0. Okay, so I'm going to be interested in the ODE that is defined over the real line. So this is the number t, and I will have a function like that. So the property of this function is that I know the derivative of this function is equal to the f of t xt. Okay, some generic function f, and this is called the ODE. And I know that the initial value is called c. That means at this point, I know this is c. Okay, right here. Okay, and the question is, let's say we have such a kind of function, and this f is given by the problem, given some specific application. The question is if this ODE has a solution or not, and if it has a solution, is the solution unique? And this is a very important question in study of, or in the research of ordinary differential equations, because given a ODE, we want to know if we are ever able to find a solution, because if the solution doesn't exist, we don't need to make any effort. And once we know the solution exists, we can consider solving it. And in practice, there are a few types of ODE that have closed form solution, but in most cases, we won't be able to find a solution, or they don't have an analytic solution at all that is proved. So in those cases, we'll be interested in finding a numerical solution, and that is a major topic in numerical analysis. But right here, we're going to just study the theoretical property when we're given an ODE, in which case we can guarantee that the solution exists and is unique. Okay? And that is actually that actually can be proved by the fixed point theorem, or Banach fixed point theorem above. And you will see how powerful that theorem is in this application. Okay, so right now, let's say that the function f, apparently the function f is a mapping from let's say we're interested in the area or interested in the domain where t is near the 0. So from negative h to h times c minus delta plus and the c plus delta. So what this means is I'm only interested in a small neighborhood right here, and I'm going to show that the existence at least in this neighborhood. If it's too far away, it would be difficult to guarantee. But at least if we're given the OD like this, then at least locally in this box, the solution should exist. Okay, and so I'm going to call this one. I denote this one by U. Okay, and this is going to be a mapping from that U to R. And let's say that this one is continuous. Assume that it's continuous, and the M is to denote the maximum value over this function over that U. Okay, so it's T x at some point in U is the f of Tx. So the M, capital M, is the largest is maximum value of this absolute values. Okay, and also we're going to assume that f is Lipschitz continuous in this second argument x. Continuous in x. What that means is for any t between negative h and h, and any x prime in this c minus delta and the c plus delta, we know that the f of t x minus f of t x prime is less than L times x minus x prime. Okay, for any t, x, and x prime, there is this. Okay, that's what we mean by the function f is Lipschitz continuous. Okay, so we have this basic setup, which is pretty usually is true in practice. So we see this 1, 2, 3. Then our conclusion is that if for this h is smaller than the smaller value of this or this. So remember that delta is the height here. That means the function is not increasing too much. This delta plus c plus delta plus c minus delta. This m, so this is the maximum value right here, and this over L is the Lipschitz constant for this f. And then if this h is smaller than that, well, it's kind of confusing that we have the h earlier here. But if this f is true for this over this region, and then we can actually make our h even smaller if we're interested in the even smaller the h, then we can keep this original f. So this f will be still defined the original h, but now we can only guarantee the h on a smaller domain, but this will be h prime. Okay, but as long as the h is as small, then if this is true, just write it this way, then we can guarantee that the ODE has a solution. The ODE is this one. It has a unique solution. Okay, for this age, for this particular age. Okay, and to show this, you can use the Banach fixed point theorem. Okay, to show that, we first give this notation definition for notation here. B bar C delta. So what this means, this is a ball centered at C with the radius delta in this space. Okay, so now this is space. This is a space of functions. For each point in this space, it's actually a function defined over the interval negative h to h. And this C can be treated as a constant function. It means that it's taking the constant value C over this interval. This delta is the radius, which tells you that if you have another point in this space, in this ball, that means it's another function. It's going to be another function, like say like this. This is the C. It's a constant function. It's negative h to positive h, and if it is a point in this ball, then that means it cannot vary too much from the C. Okay, cannot deviate from C too much, and by that we mean is that the largest deviation from the C is delta. It's delta here. Okay? So that's what this ball means. It's a closed ball right here. Okay, so if I write it formally, that means it's a set of functions such that the xt minus C is less than or equal to delta for any t in this interval. Okay, this is what this means. Okay, so I'm going to give this notation, and then I'm going to show several things. The first thing is that since I'm trying to find the solution for this, and the solution for this ODE, the x-axis solution for this ODE, if and only if the xt, you take the integral form, is equal to the initial value plus the interval integration from 0 to t for this f of t or f of s. Should change the notation right here. ds. Okay, so x is the solution for the ODE if and only if this is true. And now let's take the right hand side. I think this is t of x. Okay, and it maps this x, which is a function, to another function in this CAB. Okay, so if this point is this new function, it's the same as the original function, then that means x is a fixed point, and that's equivalent to saying that this x is a solution of the ODE. Okay, so that's our goal. And now we're going to show that we're going to define this t. So t is a mapping from the ball to some continuous function. Okay, because we're taking integral, like we showed earlier. So map a function x to a new function called tx, and tx is a function over the interval negative h to h. So for every point t, it should have a definition, and the definition is c plus the integration of f of x, sxs ds. Okay, that's our definition for this function. And apparently this function is going to be continuous. This new function is going to be continuous in t. The reason is this is a continuous function. And this is the integration of a continuous function. It must be continuous, and this is a constant. It must be continuous. So it has to be in here. And the question is, can we show that this T is a mapping from this, not to this general space, but map this one to itself. And this one, since it's a closed subset of the C, so we say that we have a complete space, and we have a closed subset of the space, and this closed subset itself forms a complete space. So if I have a closed subset of a complete space, it has to be complete as well. And we're going to show that this T is actually mapping from this to itself. Okay, so this will be our X like before, and the distance is just inherited from the distance from the C. We're going to show that T is a mapping of this to itself, and we're also going to show that T is a contractive mapping on that. And with these two, we can apply the Banach fixed point theorem to show that there is a fixed point of T, and that fixed point is a function that's solving or that solves this ODE. Okay, so that's our idea. Okay, so the first step is to show that the T is actually a mapping from the B bar to itself. It should be delta. Okay, to this end, we just need to show that after the mapping, the function is still in the ball. Okay, suppose I have a point x in this ball. That means it's a function satisfies this. It's a continuous function satisfies this. And now, let's look at after the mapping, it becomes Tx. If I want to show that Tx is also in this ball, I just need to show that Tx, the difference or distance between Tx and the C is less than delta. Okay, so let's look at the T distance between after mapping. It becomes Tx, and the distance between these two. If I can show that this is less than or equal to delta for every T, then we're done, right? So this is equal to, according to our definition for Tx, it is this. So subtract the C, that will be just become the integral itself. This becomes the integral f of s xs ds. Okay, and apparently this is less than or equal to that, fs xs ds. Okay, and because this s is between 0 and T is between negative h and h, you know that T can go to negative. We know that this s is between negative h and h, and this xs, since we know that x is a function or is a point here, so it doesn't matter what this s is, its distance from x to c is always less than delta, and that means no matter what s is, this point is always in this u. It's always in here, okay? Because s is in here and x of s is in here, and that means this part will be less than or equal to m. Okay, so that is less than or equal to m times the absolute value of t. Okay, because t can go to negative, but no matter how large the t is, it must be less than or equal to h. So this is less than or equal to m h. Okay, and we choose this h such that it is less than the minimum of these two. So it must be less than that, and that means h times m is less than delta. That means this is also less than delta. And now for every t, no matter what t is between negative h and h, this is less than delta, and that means Tx is also in the ball. Also in this closed ball, okay? And therefore, the T is just a mapping from this ball to itself. Okay, that's the first thing. The second thing is that we're going to show this T is a contractive mapping. So we know that it's a mapping from a complete metric space to itself. Also need to show that it's a contractive mapping. Okay, so to show that it's a contractive mapping, we have to do to show that for any 2 points, x, move it down to the next row, x and y, both in this ball. Then first we know that the tx, ty, there will be 2 new functions, and there are 2 points in this ball, since we know that the mapping T is from the ball to itself. So I know that, but on the other hand, I also need to show that the distance between the 2 functions should be contractive. Okay, and to show that, let's consider the distance between tx and ty. And we know that this is just the maximum of for t between negative h to h of this tx of t minus ty of t. Okay, and this is equal to I write this simply as this, less than equal to h. And this is c plus the integral, and this other one also has a c plus integral. So you to show that it's just the integral from 0 to t, f of s xs minus f of s ys ds. Okay, and then that is less than equal to the maximum t less than equal to h, 0t, f of s xs minus f of s ys ds. Okay, so because this x s and the ys, they're both nearby, they're both in here. So that means by using the Lipschitz continuity of f, you know that this must be less than or equal to L times the distance between this. Okay, so it has to be less than or equal to the maximum of this, 0t L xs minus ys. But I also know that this must be less than or equal to the distance between x and y. And this is independent of s, because this is the maximum value of xs or xt. Maybe let's use t here or s here. Y of s. Okay, so but this taking the maximum, this one is independent of s, so I can pull it out. So this is equal to that's equal to the L times d of xy times the maximum of t for this integral over a constant, but that will be just t, but t is less than h, so it has to be less than equal to this times d times h. Okay, let me rewrite that. I put t, h, and l together. But we know that this value is less than 1. because the way we chose this h, it must be strictly smaller than the 1 over L. So there has to be a number, say I call it theta, and this theta must be strictly less than 1. So now I show that the distance between after the between 2 points after mapping is less than or equal to theta times the distance before the mapping. So that means T is a contractive. Okay, so I know that T is a mapping from the ball to itself and it's contractive. So the third one is just apply the Banach fixed point theorem. We know there exists a unique x in this ball such that Tx equals to x, or in other words, xt is equal to c Tx of t, which is c plus 0 to t f s x s ds. And this means that x is a solution. Unique solution of DOD. Okay, so that proves the result.